Yes, good afternoon, team Bridges. I hope you are doing well. Let's continue brainstorming on our experience in bridge designs, construction, maintenance, and structures. Also, I will continue sharing my experience for you guys to borrow a leaf from, so that tomorrow when you are doing your further studies, you at least have where to start from. Here, I just wanted to demonstrate something in line with the question raised by, I think, Button or someone about consideration of stream flow on when you're designing the bridge. Truly, normally for bridges, pier supports are really exposed to high water currents. Therefore, the strength, the robustness, size, the depth on a water bed or on a river bed, orientations, those are factors you need to look at. And then the score depth, the score calculation. You guys who are doing water resources, I think you will also learn about how to design for water scoring. That is very, very important. Score depth normally guide the depth of foundations and also treatment required around the pier. We have local effect scoring, the local score, and then the general one, where at the end of it you combine the two to give you the overall depth of the score. So if you look at this, you consider the flow is from right to left in this direction. So when you look at the flow of water, let me see, flow of water. The orientation, normally we are going to look at around 1, 2, 3, about four scenarios. One, when the bridge pier is aligned to the floor, which is usually the case. When you see water on the road skew, then you see your pier support and the abutment are also skew. They are trying to avoid water hitting the deck, the pier at an angle. Definitely you are subjecting your deck system, pier system to a lot of force from water. So normally you have to align your support, pier support in the direction of flow. So water comes and creates a stream kind of flow, like the way you have the airfoil when it is moving through an object being blocked. It comes and creates vortices at the back. So the way you do your aerodynamics is the same thing. That same factor you use, the formula that you use for wind or aerodynamics is the same formula you use for water flowing across the pier support. The only thing is the density of air. Now you change. You use the one of water. The velocity, instead of the air, you use the one of the wind. You use the one of water, and then the drag effect. As water is going across here, it also has a drag effect. That is why if you try to tilt and you put your pier support like perpendicular to water, definitely it will not withstand. There is going to be something wrong. So that is what we have here. So for when it's at zero degree, you see this is now the flow. Now we are assuming water is flowing full, so that it has even what they call the when it's flowing full, it creates the buoyancy. So it will also lift the bridge. That's why normally when bridges are failing, on a flat effect, you see it lifted up and off it goes. So when it is flowing full, you now consider even uplift. So here is when it is at 90 degree. So when water is moving direct. Now if you tilt The software hasn't gotten the provision to have a sloping kind of forces or slanting also, which are off at an angle. So we convert it into the x and y. Then the resultant now will be generated. So I think if you tilt if the flow is blocked and start moving like about 5 degrees, then you see this is how the model is. Definitely now each of these has got a what? A x and y. So x, and y. So the resultant will be in this direction. So I'm going to simulate and look at the animation and you get to know. So that is what you need to. But normally you have to make sure you align your bridge in a way that doesn't get in blocking water. So if this has already been run, all I need is to go to view, the result, deformation. Then I have water flow at 0 degree. Definitely I have that. That's the water flow at 0 degree with a deformation. So if I apply that, that's how water at 0 degree would look like. So on plan, this is how it looks like. It tend to, and if I apply this animation, I apply, you will see that is more uniform. You can see that stress distribution is more uniform and is being split at where you have the, because these are simply supported. So this one was designed as simply supported with where you see this gap is where you have the expansion joint. Now if I change, you need to notice not the difference of the stress distribution and the angle. If you change water flow and water is blocked, one opening is blocked and water starts changing, you will see how violent the whole scenario will become. So this is now at a 5 degree. You see the movement is now moving away, is moving in this direction, while the other one was uniformly distributed. But now you can see the stress distribution. If I take you back to 0 and then you look at that, then you're going to see, you can see that is uniform. Now if you go back to 5, you will see that you have there's a bit of tilt. Then if I go further to 10 degrees, the thing become more violent. You can see so, and even if I put it back to 3, even if I put it back to 3 degrees, so where can I put this back? Let me first stop animation. Okay. So if you look at this and then you look at animation, water flow at that degrees, and then I put for you that, you can see that it's moving more to the left, and then the pattern moves in that direction. Now 15, now really we have a bridge. This bridge is it's a Moboko bridge along Kasese Hima Road. I think is being affected by water, and actually it has actually scored. When we are doing steel composite, I will show you some pictures of that and then what it is. So this one, even if it is concrete bridge, this is the scenario of dealing with water. So avoid putting your pier in a way that is blocking water. It must be in line with water so that it flows with little interference. That is what you could actually do. So if I take it back to 0, okay, let me show uplift. Now you can see the difference with the uplift. Is actually you see the entire pier is now lifting it up uniformly. So now when you look at uplift, at the same time you have a push, then the whole thing is gone. We had a problem with the Katonga bridge. For Katonga, the pier was isolated. Water came and Scour. Water went with embankment, and the thing floated, and abutment went. And then because it left a big long gap, a long span, which is like cantilever, it went down, and the pier also lifted because I think the Scour, there was a buoyancy, and the flood was too much. That's how the entire bridge came down. So that is the scenario of so if I try to have a combined, now I have a combined, if I have a combined stuff, what normally happen? Let me see. Doesn't give me that now when it is combined. So you can actually look, I think temperature effect. You can see temperature, so we still have temperature effect here. But this one basically I was only trying to demonstrate to you. I don't want to go in detail about this. Basically I was trying to demonstrate why you need to consider the angle of flow. There's a literature somewhere. I'm going to scan that and share with you, and you're going to look at it. When you tilt, let me first try to remove this. If you try to tilt this, oh yeah, this one, I think, okay. What has to be straight? If you tilt it, this face here, all that will be experiencing what's at an angle, and you have increased the surface of contact with water, and that will definitely cause problem. At the same time, you are having uplift, the bridge is being distorted, the bearings are moving, the whole thing becomes violent, and all limits will be exceeded. Boundary conditions will never be respected now at that moment, so you have to be careful. So you know, if with your fluid mechanics, we always talk about steady flow, laminar flow through the bridge. You want for water to go unnoticed, kind of stream flows, smooth to get away. That's why we do a lot of treatment around there to avoid blockage and creating turbulence. This is briefly what I could